Okay, welcome to the lectures of the chemical process. Principle, elementary principles of the chemical processes. Right, okay. On, sorry. On Monday, we talk about the two phases, right? We talk about the multiple phases system, and we introduce you some of the processes. Okay, for example, leaching, scrubbing, distillation, liquid extraction, adsorption, okay, and crystallization. These all the processes, they are all to do with the multi-phase systems, okay. And also we introduce you about this process, like phase transition process, right? So this is an important process, but it's kind of hypothetical process. So you need to think of this. Use your imagination. The process from A to B to C to D to E, and this is you can visualize this process using this example. Like there's a container, there's a piston. Okay, the piston go in, push it in, and then you will see the vapor become liquid. And you can see that these are two phases. The first drop of the liquid with vapors, and about half liquid, half vapor, and only one vapor, little bit vapor and the liquid. So these are two phases, which is in the B point, right? And if all the vapor disappear to become liquid, and this will be C point. Move to C point, and then after that, you keep the pressure as a constant, increase the temperature, so you will see gas come out. Okay, so liquid, two phases. Okay, only little bit air, little bit vapor with majority liquid, and then half vapor, half liquid, and then only one drop of liquid, and rest of them are vapors. Okay, this is in the D position, and after that, all the liquid become vapor. This will be in the C position. So this is a kind of example for the a phase transition process. I hope you understand. So after that, today we are going to talk about this very important topic. Is called how do you estimate the vapor pressure in the system? How do you measure the vapor pressure here? Okay, so the example I'm showing you here is that, sorry, I'm showing you here is that, you know, if we have these three cases, case A, case B, and case C, could you please tell me which one has high vapor pressure? Which one? Anybody tell me? Raise your hand, 0.5 point. A, B, C, which one has a high vapor pressure? A, B, or C? Raise your hand. Tell me the answer. Yes. C, right? Okay, thank you. Why? Because you have a lot of molecules in a gas phase. So this is what we call vapor pressure. The more molecules you have in a gas phase, the higher vapor pressure you will have. Okay? Right. So this is vapor pressure. So how are we going to measure the vapor pressure? So, but before we talk about this, let's have an idea of the evaporation and boiling. What's the differences in terms of the vapor pressure? So you know that the evaporation means that the molecule evaporates from the surface of the liquid. So the bubble cannot form since the vapor pressure is less than the atmospheric pressure inside. So the bubble cannot form inside the liquid. So once you have the vapor pressure is high enough, The bubble, so the boiling means what? The temperature increased. So the molecule inside this liquid is very active. They want to become gas. So the bubble will form inside this liquid. So the bubble can form and the rise since the vapor pressure can overcome the atmospheric pressure. Okay, so if the bubble come out, and this create the vapor pressure. Okay, so this is the differences between evaporation and boiling. So how are you going to measure the vapor pressure? Of course, you have a pressure gauge, so you can measure the vapor pressure. Okay, tell me what's the name of the vapor pressure? What's the name of the gauge? Anybody want to tell me? You learn this? Yes. Pudong gauge, right? Thank you. 0.5 point. You know, early bird always take advantage, right? Early bird. Okay. So you use Pudong gauge. You put a Pudong gauge in this container, and then you can see this indicator tell you what's the pressure inside this chamber. Okay. So of course, it depends on It depends on the temperature, right? If you have a higher temperature, you will have higher vapor pressure. If you have a low temperature, you will have low vapor pressure, right? And when you reach to equilibrium, the condensation rate, the molecules in the gas phase condense to become liquid will equal to the rate of the molecules evaporize from liquid to the gas phase. So we say that condensation rate will equal to the evaporation rate. At this point, we say this system reach equilibrium. Okay, so we have termed something like this. So let's use water as an example. If you have water in a container, which is a closed system, it's sealed. Okay, the container is sealed. So the water and depends on a different temperature and pressure, you will have different water vapor pressure, right? Okay, so what's the pressure related to the volatility? What is volatility? For example, if I tell you water and alcohol has different volatility, right? Okay, so what is the volatility? The volatility of a species is the degree to which the species tend to transfer from liquid state to vapor state. So the vapor pressure is what? Vapor pressure of the species is the measure of its volatility. So if the volatility is high, and vapor pressure will be high. Okay, so let's use water and ethanol or alcohol as an example. Which one is the volatility is high? A, water. B, alcohol. Which one? 0.5. Yes, alcohol, right? Thank you. Piece of cake. Thank you. It's very good, right? Okay, get points. So you have higher volatility, and that means what? Alcohol is easy to vaporize compared to water, right? Of course, when you have injection, right, and then they use alcohol to clean the surface of your skin, and you feel cold because what? Because alcohol take away the heat from your body, from your skin, and it can vaporize very easy, right? So, okay, so. And the vapor pressure, we use P star over T. P star function of T to represent vapor pressure. So P star over function of T is the vapor pressure of a pure substance. Okay, please remember this P star function of T. So how are you going to estimate the vapor pressure? Of course, you can measure it, right? Or you can check it from the table. For example, you can check the vapor pressure of the water at 25 Celsius. You can check the vapor pressure of alcohol at 60 Celsius, right? Okay, you can check this vapor pressure from a table. or you can measure it, or you can calculate by according to equations. Okay, so here we are going to introduce you two equations. The first one is called Krypton equation. The second one is Clausius-Krypton equation. Okay, first let's go to the first Krypton equation. So this is Krypton equation. Okay, you don't need to remember this. If this show up in your final exam, I will give you this equation. So this equation is kind of, what is this? As you remember, I told you that the vapor pressure is a function of temperature. So temperature change, vapor pressure change. Okay, so this is this differential equation. Differential equation dP star divided by dt is equal to delta HV over carat divided by T Vg over carat minus VL over carat. So what are these symbol for? What are these symbol? So P star here is the vapor pressure of a pure substance. Okay, and divided by T. T is the absolute temperature. You use Kelvin as a unit. Okay, delta HV over carat. Why is this? You know, over carat means what? Divided is a per mole, right? You regardless of the amount of the substance. So H is kind of latent heat. H is latent heat of vaporization, and by per 1 mole of the substance. Okay, so V stands for vapor, right? So this is called latent heat. And what is latent heat? In Mandarin is 潜热. Okay, energy required to vaporize 1 mole of liquid. So you have 1 mole. Okay, to be defined more precisely in chapter 8. But anyway, I'm going to show you a video to let you know what is latent heat. And Vg is specific molar value of gas. And VL over carat is specific molar value of liquid. So this is the value of the gas in the gas phase. This is the value in the liquid phase. Okay, this is called Krypton equation. So as you know, we use water as an example. You will see that there's a liquid water, water vapor, and different temperature and pressure. Okay. So, this page showing you that using this equation, we want to determine the heat of the vaporization. That means we want to measure latent heat. I think I better show you what is latent heat first. Latent heat is what? Latent heat is once you change the phase from solid to liquid, how many energy required to give this system in order to change the material from solid phase to become liquid phase. And temperature doesn't change. And also, if you use H2O as an example, you want to melt the ice become water, and per 1 gram or per 1 mole, how many energy required? And this is what we call latent heat. Okay, and also if you have a liquid, how many energy required to vaporize liquid water to become vapor, and per mole, and this is what we call latent heat. Okay, and interesting thing is, if you increase the temperature, or if you get energy, and then the phase change from solid to liquid, or from liquid to solid, from liquid to gas, but temperature doesn't change. Okay, so that's why I'm going to show you here what is latent heat. So latent heat is the energy required to change the phase from solid to liquid, or from liquid to gas, right? Right, so how are you going to determine the latent heat of the water, or for the alcohol, for example? So how do you determine the latent heat, the heat of the vaporization? So here, that if the pressure if the pressure is not so high, and we can assume two conditions. The first is that the gas, the value of the gas is much larger than the value of the liquid. So we can regardless of the value of the liquid. So Vg minus VL will become Vg. So you remove this term. And we assume this follow the ideal gas equation of state. So Vg equal to RT divided by P star. Right? Okay? So you can simplify this equation, okay, by these two conditions. Okay, the first one, you remove this term, so you become like this, right? Okay, and then you replace Vg over caret to become RT divided by P star. So this equation becomes something like this. And you put the pressure together and temperature together, so you got something like this. You have pressure together and temperature together. You just rearrange this equation to become like this. Easy. And now you know what's going on, because this is differential equation. So as you know, if you see this differential equation, you just do something simple. So you can rearrange something like this. So d natural log P star divided by d differential, right? And reciprocal of T equal to this minus delta H over caret divided by R. So this is the modification of the Krypton equation according to these two conditions. Okay, so how are we going to use this equation to estimate or to determine heat of the vaporization? How can we use this equation to determine the latent heat? Okay, so let's do this again. This equation, Krypton equation, we do the simplify this equation according to these two conditions, right? We get something like this. So when you see this, you might say, well, if I regard this as a delta here, so I just know that if I plot dp natural log P star as in the y-axis and then reciprocal of T in the x-axis, so this becomes what? This has become a slope, right? This becomes a slope. Okay, this becomes a slope. So if you have two data, you have 2 points here, because this represents a line. We learned this in the chapter 2, right? We learned this in chapter 2. So if you have 2 points, you can plot a line. So the slope will be this one. You can get, if you get a slope, if you have 2 points, which you can see that P star and temperature, P star and temperature, you can plot a line and you can get a slope. And once you got the value of the slope, you can get latent heat according to this equation. Okay? So what you need is do experiment and measure 2 points, two different temperature and pressure, 2 points, and get the latent heat. So if the vapor pressure of a substance is measured at the several temperatures, okay, you change temperature, you got the vapor pressures. So you can plot a few dots, a few lines, a few points along this line. So the natural log P is plotted versus reciprocal T, the slope of the resulting curve at a given temperature equal to this one. So you get latent heat because R is constant, right? Okay. So this is the method mostly common used to determine heat of the vaporization experimentally. So basically, you need to do experiment. You found points along this line, and you plot a straight line and get the slope. You get the latent heat. Okay. So please, you need to practice by yourself. We will have a example for you to exercise. Okay, so the first one is to determine the latent heat. And now I'm going to introduce you another equation called Clausius-Krypton equation. Okay, this is Krypton equation, right? Okay, and then again, we use these two conditions to simplify this equation. Can we? Yes, we can, right? Okay, and then now let's change to put the pressure on the right hand side, and then to put the left hand side and put the temperature on the right hand side. So you will rearrange this equation become like this. Okay, and then this is differential equation, right? So, and you know that this is differential equation in both sides. We can integrate this. So if the heat of the vaporization of the substance is independent of the temperature. So if you integration of this equation in both sides, and then this one is independent of temperature. So you can take this, you can use this as a constant. So once you integrated this, you will get equation like this, right? Okay. Right, so according to Krypton equation, this one, you can find out latent heat experimentally. And then if you have pressure and temperature, what you need to know is what? A constant B here only. Okay? So once you find out constant B, then you will know the relationship between the pressure and temperature according to Clausius-Krypton equation. Okay. So you can see that the vapor pressure is function of temperature, right? Vapor pressure is function of temperature here. Okay, so Krypton-Clausius equation, let's move forward. A plot of the natural log P star versus reciprocal T, or we can use semi-log plot, right? Semi-log plot or use this is the same thing. I hope you remember this when before we are in the before the midterm exam. We learned this before. So this is what we learned in order to get latent heat, right? And then a straight line, this is a straight line, right? Y equal to AX B plus B. So the Y will be natural log P star. X will be reciprocal of T, right? So you get this equation, we got slope when we get this latent heat. And intercept will be got the B here, right? Okay, so this is what we learned from Krypton equation. And we'll get the latent heat from the Krypton equation. Okay, so now you have this number, so you can put the latent heat into the Clausius Krypton equation here. And what you need to know, what you need to get is the constant B using the Krypton-Clausius equation. So get B, what? From the Clausius-Krypton equation. Okay, you know this, and you do experiment, you can get P star and the T temperature. You can get a vapor pressure and temperature. So of course you can get B using the Clausius-Krypton equation. So this equation will be completed. You know the latent heat, you know the constant. So once I tell you, if I give you one number, temperature, for example, I ask you water, H2O at 300 Kelvin, and then what's the vapor pressure? So if I tell you this, you know the temperature, you know the latent heat of the water, you know the B constant, you can calculate vapor pressure according to Clausius-Krypton equation. Okay, so this is example. This example is 6.1-1 vapor pressure estimation using Clausius-Krypton equation. So here is that I give you 2 points. Benzene at T1, you got P1 star. P1 star is the vapor pressure of the benzene at temperature T1, right? P2 is the vapor pressure of the benzene at the temperature T2. So they are like this. They are 280.8 Kelvin, and the vapor pressure is 40 millimeter mercury. Okay, and then temperature here is 288.6 Kelvin, and then vapor pressure is 60 millimeter mercury. And then this example asks you to find out latent heat, and then asks you to find out B from the Clausius-Crispin equation. So you can get this easily, right? Why? Because 2 points, you can get a straight line. If you get a straight line, you can get a latent heat. So once you get latent heat, you put a latent heat, the value of the latent heat into this Clausius-Crispin equation. You got this, and you put this one of this number, temperature and pressure, into this equation. You got B constant. Okay, once you got B constant, and now I say that, wow, now the temperature is 42.2. I ask you for the vapor pressure of the water of the benzene at temperature 42.2. So you just put this number here, right? And you already know the latent heat of the benzene. You already know the constant B, so you can get the vapor pressure, P3. Okay? Understand? Are you with me? Anybody home? Hello, anybody home? Are you sleeping? No? Okay. So if you don't understand, or if you want to know more details, please come to me after lecture. Okay? But what I really suggest you is go home and really do the practice. Okay? And you can, if you don't have textbook, you go to library to borrow one. And this the solution is all in the library, all in the textbook. So I just write something easier here for you. So please do the practice. So the question is very simple. I give you 2 points. I give you temperature 1 and temperature 2 of the benzene. And I already give you the vapor pressure of the temperature 1 and vapor pressure of temperature 2. And now I ask you for the temperature 3. And I want the vapor pressure at the temperature 3. So you need to find out why is this. But before you find out this number, you need to find out latent heat and the B constant. So the answer is 207. Okay, so this can be this. So I give you these 2 points, and I want you to find out this point. So you might say, "Well, Professor, this is not a straight line." Of course, this is not a straight line, right? Because this is not a log plot, right? You have to change this to become log plot. You will become a straight line, right? Okay. Right. So once we understand Crispin equation and Clausius-Crispin equation, we have something easier for you to find out the vapor pressure. Okay, this is what we call Koch chart. And another equation is called Anthony equation. So this is Koch chart. Koch chart is that this is temperature, and then this is pressure. Of course, you understand this is log plot. It's a straight line. Here is that I give some examples. The P star function of T is here. Okay? And then I give you an example. This spot is what we call critical point. You cannot reach more than this temperature and pressure, right? This is supercritical. This region is called supercritical state. So in the case of water, as you can see from here and then go down to here. So you can see that this is a line, and you know that, as we know that the water has a critical temperature and critical pressure. So this is critical temperature, which is 374.3 Celsius. And this part is 218 atm. Okay? And of course, if you reach the 0 Celsius, there's no vapor pressure anymore. Okay, so you can use the Koch's chart to find out the relationship between the vapor pressure and temperature. So this is the case of water. You can use the case of any other things like ethane or ethylene or propane, something like this. Okay, and one of the extreme cases is mercury, because mercury is a very heavy liquid, right, in the atmospheric pressure. Okay, so as you can see, this will be in the right hand side of this Koch chart. Right, and next one I want to introduce you is Anthony equation. Anthony equation is also another equation that related to the temperature, which is the vapor pressure is a function of temperature, right? Okay, so we don't use natural log. We use normal log here, and then equal to A minus B divided by T plus C. So ABC is a parameter, which is a constant. Okay, so you need to find out this ABC from a table. Okay, you have different species. You have different value of the ABC. So Anthony equation is a relatively simple empirical equation. Empirical equation is that once you do a lot of experiments and you try to fit A, B, C in this equation. So that means that empirical equation means that you do a lot of experiment and then you need to find out an equation related to this experiment. Okay, so that's what we call empirical equation. It's not from theoretical study or theoretical study, and you create equation. Okay, so P is the pressure. We use millimeter mercury as a unit. T is temperature. We use Celsius. And A, B, C for several compounds are listed in table B.4. Okay, so the next page is going to show you some of the example of the Anthony equation, the constants of the Anthony equation, A, B, and C. So as you can see, that Anthony equation is this, right? And then the compound is here. The formula, of course, you know, but for the ABC is suitable for the range. For example, this is minus 0.2 to 34.4 Celsius. And this species, this compound suitable for A, B, C can be used under this range of the temperature. Okay, so here, if this show up in your final exam, I will give you this table. And you need to find out A, B, and C. Okay, so here I just want to give you some example of water. So water here, there are two types of the ABC. One is in the range of 0 to 60. The ABC will be 8.1, 1,750, and then 235 here. So this is, if you want to use these three constants, this temperature need to be in the range of 0 to 60. If the temperature is in the range of the 60 to 150, then you need to use ABC in this with these three numbers. Okay? Easy, very easy, right? So once you know the temperature, I tell you, I want you to find out the vapor pressure of water at temperature 30. So you know that, oh, it's 30 is here, right? So you just put 30 here, okay? And then you put A, B, C using these three numbers, and you using your calculator to find out P star. The unit is millimeter mercury. This is easy, right? Wow, this might be the Kahoot next week, right? Okay, this might be the Kahoot next week. If you use calculator, that will be very easy. Okay, Well, I don't know. I just have a thought like this. Right, so now let's summarize what we just learned. For a single component phase equilibrium, liquid to gas for P star, actually, we start to learn Krypton equation in order to find out latent heat, right? And then Clausius Krypton equation, we need to find out B, and then now we already have a very good, because this differential equation is difficult to get to find out the answer. So if you use this equation, Clausius Krypton equation, now it'll be easy for you to find out any vapor pressure according to different temperature, right? Once you have latent heat and constant B. And then we already told you that the cost chart, you can have temperature related to the vapor pressure in terms of different substance. The Anton equation is called empirical equation A, B, and C. Okay, so these are the one I just introduced you today. So please remember this. So latent heat is a very interesting topic. Why? Because latent heat is kind of energy, right? The energy required to change the phase. So imagine if you have water, ice, and change to water, it requires 333 kilojoule per kilogram. This energy requires 1 kilogram. 1 kilogram requires 333 kilojoules. And using this same energy, you can increase the temperature from 1 Celsius to 80 Celsius. So as you can see, this energy is very huge. Energy is very huge. So that using this good stuff, we can have a very nice thinking to design a kind of material, what we call phase change material. Phase change material is what? For example, this is a wall. This is a wall. And we put the phase change material into this wall. And then once the sun hit this wall, when the sun is very strong, the sun this is, for example, this wall is concrete, right? And the concrete, the sun hit this wall, and the heat will deliver from outside to the inner side of the wall. So in the room, you will feel very hot. So what happens if there is some material which absorbs the heat from the sun and block the heat in order to avoid the heat going into the room? And then the temperature doesn't change. The temperature of the wall doesn't change. This is good, right? And then in the winter or at night, the temperature dropped. The temperature dropped and the heat released out. So this is very good wall. So this is a very nice materials, right? And why the energy cannot go into the room from outside? Why? Because the phase change material absorb all the heat. And then while they absorb heat, they don't increase the temperature because phase change from solid to liquid. And at night, from liquid to solid, and release the heat out. Okay, so this is one of very good materials, but unfortunately, it hasn't commercialized. Okay, especially this is a very good material. Okay, you use your knowledge to design this kind of nice things. Right. Okay, so we finished the section 6.1, and before we move to the section 6.2, the Gibbs phase rule, let's refresh ourselves, right? Okay, let's play Kahoot. And the title of the Kahoot is what? Separation process. So in the beginning of chapter 6, we have separation process, right? Separation process. Right. So let's move to section 6.2, the Gibbs phase rule. you know that if you mix the two phases, it's very interesting because you don't need all the information to create the system because it's kind of related. These two phases are related. So this page showing tell us that duplicate the system for two systems like gas or liquid. So when two phases are brought into a contact with each other, a redistribution of the compounds of each normally take place. Okay, blah, blah, blah. Anyway, I just want to tell you that this is the system which has two phases, and gas and liquid. So assume there are three compounds, A, B, C compounds, distributed between the gas and liquid phases, A, B, C. So A will be in liquid phase and as well as in the gas phase. B will be in liquid phase as well as in the gas phase. C the same thing. Okay, C is the same. And then under different temperature and pressure, and the amount of A species in the liquid phase and in the gas phase will be different, of course, because you change the temperature, the vapor pressure will be different for A species, or for the A compound, or for the B compound, for the C compound, the same. Okay? So if we fix the temperature and pressure in this system, and we will get the fraction of the A compounds and also the fraction of the A compound in the gas phase and a fraction of the A compound in the gas phase and also in the liquid phase, right? And also we will have fraction of the B in the liquid phase as well as in the gas phase. Okay, and we also will have fraction of the C, or especially molar fraction, I should say, molar fraction of the C in the liquid phase as well as in the gas phase. Okay. So if you want to provide sufficient details for someone who can duplicate this system exactly, so how many information I should give you? For example, if the words showing you here is all unknown, right? This words in the red color normally is unknown, right? So how many information I should give you in order for you to duplicate this system? For example, should I give you the temperature, pressure, masses of each phases, and the value, density, fractions for each phases? Should I do this for you so you can duplicate this system? Or I just give you some of the information because some of them are not independent. For example, if you only have three spaces here, do I need to give you XA, XB, and XC? No, I just give you two out of these three. So another one will be what? Will be the one minus, if I give you XA and XB, you can get XC. Why? Because XA, XB, XA plus XB plus XC will be 1. So I don't need to give you XC. I just give you 2 out of these 3. Right? The same as Y, the molar fraction in the gas phase for all the components. So, however, these variables are not all independent. So how many information I should give you? That's what we call degree of freedom, right? How many degree of freedom you will have? If you don't have degree of freedom, that means all the number is fixed. If I give you a degree of freedom, that means you have many degrees. The number is not fixed. So do you provide sufficient information? Okay, so before that, we need to know 2 categories of the variables. And then, of course, we already discussed this before in chapter 4. We talk about dependent, independent, like dependent species, independent species, dependent equation, independent equation. Okay, so intensive variables depends on the size of the system. Normally, we don't talk about this because if the size is big, then value is big, the mass will be large. So normally we don't talk about this. We talk about intensive variables, not dependent on the size of the system. like temperature. Temperature here will be temperature in this corner will be the same as temperature in that corner. It doesn't matter. It doesn't matter which the size of this room, right? Also the pressure. So this is not related to the size of the system, and also the density, specific volume. These are all intensive variables and fraction, right? So what we want to discuss here is intensive variables. Okay. So this section we want to discuss is the degree of freedom in Gibbs phase rule. So in the chapter 4, we already learned degree of freedom. But in chapter 6, we especially want to know the degree of freedom in Gibbs in two or three different phases. So ladies and gentlemen, please remember this one. So degree of freedom is how many pieces of information you needed in order to take calculation. This is in chapter 4, we learned this already. So the numbers of the intensive variables that can be specified independently for a system at equilibrium. Chapter 6. So the meaning of the term degree of freedom in the Gibbs phase rule is similar to its meaning in the degree of freedom analysis in chapter 4. That's the same. So if the degree of freedom equal to 0, that means all the number is fixed. All the value is fixed. Okay? So in the Gibbs phase rule, the degree of freedom equals the numbers of intensive variables that must be specified for a system at equilibrium. Ladies and gentlemen, remember, it needs to be at equilibrium state. Otherwise, it doesn't make any sense. Okay? So you need to be in the equilibrium state before the remaining intensive variables can be calculated. So I want you to remember this. The Gibbs phase rule, the first one, if no reactions occur among the system compounds, the Gibbs phase rule is this one. dF equals to 2 plus C minus pi. What is C? What is pi? dF stands for degree of freedom. C is the number of the chemical species. Pi is the number of the phases in the system at equilibrium. So here I want to, so if R independent reactions occur among the system's components and the reactions proceed to equilibrium, then you need to add R here. You need to minus R here. Okay, if there is a chemical reaction. Okay, and then independent reactions. How many independent reactions? 1 or 2 or 3, and you put a number here. Okay? Right. So let's do a little bit practice. So example 6.2-1, the Gibbs phase rule. So determine the degree of freedom for each of the following systems at equilibrium. Okay, first one, pure liquid water. You have one. So this is a phase diagram, right? Phase diagram. Okay, so what's the degree of the freedom for the pure liquid water? C, how many? C is what? C is component, right? So how many components of this in this system? Pure liquid water. Only water, right? So H2O, right? Only one. How many phases? So pure liquid water, so only liquid, so 1. Right? So if you have 2 plus 1 minus 1, that equal to what? Equal to 2. Okay, so what does that mean? If it's equal to 0, that means the number is fixed, right? So the 2 means what? You need to still have 2 variables in order to fix the system. So what are these 2? If you have a phase diagram here, what are these 2? So this is in the liquid phase, right? So it can be anywhere. The system can be anywhere in this region. Because what? Because you haven't fixed the temperature and pressure. So you have two variables. So degree of freedom is 2. They are pressure and the temperature. So once I tell you 100 Celsius, 1 atm, and you realize it's somewhere around here. The point is here. So I tell you I fix the temperature and pressure for you. Sorry, I should say 90 Celsius and 1 atm. So you'll know that, wow, Professor, if you tell me the temperature is 90 Celsius and 1 atm, I know exactly where this system is in the phase diagram. Okay? So two intensive variables must be specified to fix the system. For example, temperature and pressure. Okay, how about this one? A mixture of liquid, solid, and vapor water. Wow. So degree of freedom is 2 plus C minus pi. So how many components here? How many components here? 1, right? 1. Only water, H2O. Only water. So 1 component. How many phases in this system? Liquid, solid, and vapor. So how many phases? 3, right? Solid, liquid, and vapor. So 2 plus 1 minus 3. Degree of freedom is 0. What does that mean? The value is fixed. The position is fixed in this system, in this phase diagram. Where is this? Please tell me where is this? This position. A, right? In the A position. Why? Because there's only one point here. The liquid, gas, and solid of the H2O can coexist, which is in the A point. So no further information about the system may be specified, and all the intensive variables are fixed. It's here. Okay? So this is triple point, a fixed pressure and the temperature. Okay? Right. Okay, so another example, let's practice a vapor-liquid mixtures of acetone and MEK. You know acetone and MEK, right? They are mixable. They can mix together. You know, the liquid-liquid traction, we use this as an example. So acetone and MEK is here. And I give you different, you know, the word I mark in red color tell you this is unknown, right? So at this point, we know that there's a molar fraction. If you change the temperature and pressure, you have different molar fraction in the liquid phase for the acetone and MEK. So if XB is unknown, XA will be known. Why? Because XA plus XB equal to 1, because this is called molar fraction. And how about in gas phase? We use YA and YB. A stands for acetone, B stands for MEK, for example. And again, YB, if YB is unknown, YA will be known. Why? Because YA plus YB equal to 1, molar fraction. Okay? So you will know that there are 4 unknowns in this system. So so you have 4 unknowns in this system. So let's see the Gibbs phase rule. The DF is 2 plus how many? C. What is C? How many? 2, right? Acetone and the MEK. How many pi here? Phases. 2 phases, right? What? Gas and liquid. So another 2. So DF will be 2. What does that mean? You have 4 unknowns. Normally you have 4 unknowns in this system. And then you just need to know another 2 out of these 4. Then you can get another 2. Why? This is gas phase rule. Okay, so in this case, if I give you another condition, another 2 numbers, for example, temperature and pressure. If I give you temperature and pressure, you can get this YB and XB. Okay, and if I give you temperature and the XB, you will be able to get YB and pressure. So you can duplicate this system. Okay, two intensive variables must be specified to fix the system. And then, for example, setting T temperature and pressure fixed the acetone and MEK mole fractions in both the vapor and the liquid phases. Okay, if I give you temperature, the number of the temperature and pressure, and then you will get molar fraction of B and in the gas phase, and molar fraction of B in the liquid phase. Magic, right? Oh, because not actually it's not magic, because we have some equations, and we are going to introduce to you these equations. So that means what? I tell you the temperature, pressure, so you can get this too. Okay. Right. So let me summarize the section 6.2. First of all, phase diagram tell you this, only one single component. We can use phase diagram to realize this system, right? Okay, and we know that the vapor pressure and the volatility, you know, the vapor pressure is related to the volatility. Volatility is high, vapor pressure will be high. And how are you going to estimate the vapor pressure? Single component, I told you already. Krypton equation, Clauser's Krypton equation, and Anton equation, and Koch chart. So you can use these two tools to find out the relationship between the temperature and the vapor pressure. And then we learn Gibbs phase rule. Please remember this. You have to remember this very well. This might be the Kahoot next week, right? Okay, Gibbs phase rule. Right, so we finished the section 6.2. Okay. It's getting excited. It's getting more interesting. And you never learn this when you are in high school. So it's fun. It's fun. So we are going to talk about two phases, and then a very special case, and also is a easy case for you to firstly to understand the condition. So the section 6.3 is gas liquid system, and this is special case, and also is an easy case, which is only one condensable component. So what does it mean, one condensable component? For example, in the gas phase, you have water, nitrogen, oxygen, argon, helium, for example. But only one component can be condensed, which is water, right? In this case. So if I give it different temperature and pressure, and then I want you to tell me how many waters in the liquid phase, or what's the pressure in the gas phase of the water in the gas of the H2O, or what is the molar fraction of the H2O in the gas phase. So of course, if you have different components, you will have different molar fractions, like YH2O, YN2, YAR. AR is argon, okay? However, because this case is only one condensable component, so water is only one, can be condensed. So the molar fraction in liquid phase is always 1. There's no 0.9 or 0.8 because it's only one condensable water. Okay, so we are going to talk about this case. We only have 10 minutes, so I just tell you briefly. So one condensable component is that we have A, B, C, D, E, F in the gas phase, and only one A component can be condensed. Okay, just now I just show you this. So I wrote this as a kind of in red color, and you know that this is unknown, right? This is unknown. So the system containing several components, of which only one is capable of existing as a liquid, and the process conditions are commonly in the industrial processes. Okay, this is one of the important industrial processes. Okay, like gas condensed become liquid. So if gas condensed become liquid, we call condensation or dehumidification. For example, if this is water, right? Dehumidification. Why? Because water condensed, that means you make the air very dry. So that's why we call dehumidification. Okay? How about if the water goes up from liquid to gas? This kind of process, what do we call it? Evaporation. Okay? Or drying. For example, if you have a slurry, or if you have a kind of brick and have waters, and water come out, and we call drying, right? Drying. So this is the case. Components in a system can be this system, right? Can be this condition. Right, and here I want to tell you a kind of, use your imagination to realize this example. So at time equal to 0, in the very, very beginning, this is a dry air, and temperature is 75 Celsius, and the pressure is 1 atm, which is 760 millimeter mercury. Okay, and then at this moment, the vapor pressure of water is 0 because there is no water. There is no H2O in this system. Okay, and now I pour a liquid water into this system. And of course, you have some waters remain in the system, right? This is not time 0. At this time, this water evaporates. So the time is larger than 0. And you will start to have vapor pressure because why? Because different temperature. Right? 75 is very hot, so water will vaporize. So you have water in the gas phase. And of course, the vapor pressure will be larger than 0. When we talk about vapor pressure of water, that means we want to think of how many water molecules in the gas phase. If you have more water molecules in the gas phase, that means what? Your vapor pressure will be high. Okay? Okay, and once time goes by, and then the water will drop, the amount of water in liquid phase will reduce until it reaches to equilibrium. The vaporization rate will equal to the condensation rate. The vaporization rate of the water from the liquid phase to gas phase will be equal to the condensation rate of the water from gas phase to the liquid phase. And this is what we call saturation. And the time, we can use T saturated. So it might go for a period of time, for example. And of course, you see the level of the water reduce, right, from the beginning. So this is called saturated. So what does it mean, saturated? Saturated is no change occurs in the amount of the composition of the either phases. Okay, so in the gas phase, the amount of the liquid of the water doesn't change, and the amount of the water in the gas phase doesn't change. So this gas phase is then said to be saturated with water. And at this moment, this moment, the water is called saturated vapor. Saturated vapor. And this system reach equilibrium. Equilibrium. Okay? Okay? So you can have different temperature and pressure. You can play this around. You can change to different pressure and temperature. Okay, but at this moment, of course, the molar fraction of water is always 1. But depends on different temperature and pressure, the molar fraction of the water in the gas phase will be different. And now I want to ask you, how different? What can we get this number? Or can we get partial pressure or vapor pressure? And I hope you still remember in chapter 5 we learned Dalton's law. Dalton's law means what? The partial pressure equal to molar fraction times total pressure. So this chapter 5 in Dalton's law, we have total pressure, and if we know the molar volume of the water in the gas phase, we will know the partial pressure. Vice versa, if we know the partial pressure of water in the gas phase, we know the total pressure, then we know the molar fraction of the water in the gas phase. Okay? So this is important. I want you to remember this. So DOF is variables, temperature, pressure, and the molar fraction. And you might say, well, Professor, why you didn't write down partial pressure of the water? Because we know that if you know the molar fraction, you will know the partial pressure of the water because according to Dalton's equation, right? Dalton's law. Dalton's law here, right? Dalton's law. So you don't need to write two of these in this case. You just want to know the molar fraction. Okay? Right. So the three variables: molar fraction, pressure, and temperature. So what's the Gibbs phase law? 2 plus C, how many? 2, right? Because it's air, right? Air and water, there are 2. How many phases? 2. So the answer is 2. So you need to know 2 variables out of these 3 in order to get the rest of it, another one. Okay? So how are you going to get that? So only 2 out of the 3 intensive variables, Tp and the molar fraction of the water, can be specified. Some relationship must be exist that unequally determines the value of the third variables once the first 2 have been specified. So you must have a relationship between these 3, so that if you have these 2, you can get this one. So which one is this? Okay, and once you get this one, you get this one. Why? Dalton's law. Okay? So what are these? If you get this one and this one, can you get this one? What kind of equation you need to follow? Ladies and gentlemen, Law's law. Law's law. Law's law is this one. YI capital P is equal to vapor pressure of the I species function of T. So I think we run out of time today because this Law's law is very important. I don't want to talk this more. So I want to leave this here. So next week, we'll start to talk about Law's law. So as you can see, Law's law is related to what? Temperature, pressure, and molar fraction. So temperature, pressure, and molar fraction. So this is equation. If you know 2 of these, you can get this. Okay? Right. That's it for today. I hope you enjoyed the lecture today, and I will see you next week.